We're going to look at a displacement time graph for multi-stage or a multi-stage displacement time graph. Right? Multi-stage meaning that the way that the displacement changes is going to be different at different parts in time, right? And this is because the way that our velocity is interacting with our displacement is changing. So in the example here, we can clearly see we have two distinct periods of different velocity. The first 5 seconds, right, is constant velocity. And the next 5 seconds until rest, we can see that we have deceleration, meaning we have changing velocity until the car comes to a complete stop. So we're going to have two different stages that we need to work out, and we need to work both of these stages out separately initially, and then we're going to combine them at the end, all right? So we need to keep track of our notation, right? At the end of the day, we need to combine both elements together, right? And we want to not only graph this, but we want to create equations that we could input a time value and we could get a displacement value out, okay? In other words, we want an equation for displacement in terms of some time function, okay? And that's going to be the main displacement and main time functions. Now, we need to first work out these things separately. So let's do stage 1 first. Okay, here's stage 1. This is the constant velocity stage, right, where we had the same velocity. When we have constant velocity, we can just use the constant velocity equation. And before we work out anything, we are going to set the information that we have, and we're going to then select the appropriate equation. So I'm going to call the first time T1 to distinguish it from stage 2. And that was given to us as 5 seconds. And that is all the information we were given. And we were given the velocity as 60 meters per second. When we're dealing with constant velocity, we can just use the formula displacement equals velocity times time. And plugging in our information, right, we are going to solve for displacement 1. This is the first displacement that's going to happen. This is not the total displacement. This is just displacement 1. Right? And this should not be D. This should be displacement. This is the unknown that we're trying to solve. So plugging in our variables, displacement 1 is equal to velocity, which is 60, times time, which is 5. This gives me a displacement of 300 meters. At this point, we can go to the graph, right? We can see that at 5 seconds, we have a displacement of 300 meters. Because we have constant velocity and because velocity is gradient, a constant gradient tells me that we have a straight line. And so we can just graph for ourselves a straight line, okay? Now this is a graph and all graphs come with an equation. So we need some equation that if I place in any time value for the first 5 seconds, it will give me the displacement, right? This is just a straight line that goes to the origin, okay? We can just use our displacement time, right? Because we know the velocity, it's constant, right? So the velocity is just going to be 60. So my function, right, displacement, this is the main displacement, is equal to 60 t. Now, very importantly, there's going to come a change in velocity after 5 seconds. So this equation is only valid from 0 to 5 seconds. Okay, this is called a piecemeal function. It's a function where at different stages for your input value, you will have a different function. So between the values of time equal to 0 and time equal to 5, you need to use the equation displacement equals 60t, and that will give you the displacement at that time. Now, after 5 seconds, the way displacement happens is going to change, and so we have stage 2. Now we want to distinguish stage 2 from stage 1. So we're going to call time 2, right? And this is unknown at this stage. We know the initial velocity at 60 meters per second. We know that deceleration is 3 meters per second squared. That's why it's negative acceleration. And we know we want the final velocity to be 0, okay, because the car comes to a rest. So at this point, we would like to find where the displacement is and how long it took the car to come to rest. Now, we always like to use equations that rely on the information that we're given. And based on the information that we are given, we will select this formula, okay? Velocity equals initial velocity plus acceleration times time. So I'm going to plug in all my variables, right? Velocity is 0. Initial velocity is 60 meters per second. Acceleration is minus 3 meters per second squared. Time is going to be time 2, very important. Solving for that, T2 is going to give me 20 seconds. This tells me the second stage is 20 seconds long. Now we just need to find the displacement. Now we could use the time that we've just worked out to help us with displacement, but we don't like to rely on that. We rather use an equation that uses the information that we've already been given. Okay? And based on the information we're given, we can use the formula v squared equals u squared plus 2as. This doesn't rely on the time, because if we got the time wrong, we would now get the displacement wrong. Let's place in the values that we know. We know the velocity at the end is 0. The initial velocity is 60 meters per second, and that's going to get squared. Plus 2, the acceleration is minus 3, and the displacement is displacement part 2. Okay, displacement 2. That gives me displacement 2 equal to 600 meters. So now we have how long stage 2 took place, and also how much displacement took place in stage 2. So if we had to completely ignore the first 5 seconds, right, and we pretended for a second that this was the starting point, because remember we're starting here, our displacement after that time would be 600 meters, right, and our time would be 200 meters. So if we want to find the total displacement and the total time, right, we can say that the total time is equal to, well, the first time plus the second time. This is going to give me the 300 meters from the first time and the 600 meters from the second time, for a total of 900 meters. And this is not time, this is all displacement, sorry. Now going to the time, the total time is equal to time 1 plus time 2. That's going to be the 5 seconds from time 1 and the 20 seconds from time 2. And this will give me 25 seconds total before the car stopped. Now we could go plot this on the graph if we wanted to. We could go to 25 and to 9, and we could mark where this occurs, right? Except this did not occur with constant velocity, so it's not a straight line. We can't draw a straight line from 300 to 900 because the gradient was constantly changing. Okay? Constant velocity, the gradient remains the same. When we have constant acceleration, it causes the velocity to change. So in order to work out what to draw, we need to come up with an equation for the second part of the journey. Okay? And this needs to be based off the starting position at the end of stage 1. Okay, so stage 1, we ended already at 300 displacement, and we ended after 5 seconds. So we are now trying to solve this part here. We are trying to find an equation from time 5 to time 25. So in terms of our displacement function, we know that this total displacement, right, that we started off with, okay, at this point is now equal to the displacement of stage 1 plus the displacement of stage 2, okay? Stage 1 ended at 300 meters. So we're starting at 300 meters regardless of what happens in the second stage of our displacement function. What we need to do now is also look at the time, because the time also doesn't start from 1. So my total time is equal to time 1 plus time 2, and my time 1 is at 5 seconds. So for the second stage of this function, we're already starting at 5 seconds. What we need to do now is create an equation including these two variables, right? We need to change those into something that relates to the main function, okay? And what we'll do is we're going to change this t2 equal to t minus 5, right? Let's first find a function for S2, right? We would like to create a function that is displacement with respect to time, just like we did for the first stage. We had displacement equal to 60t. If I put in a value for t, it would give me a displacement. I would like to do the same thing for the second stage. So I'd like my displacement and my t to remain in place, okay? And the only other variables we are given are initial velocity and acceleration. But that's enough to use this equation to find a function, okay? ut plus a half at squared. Plugging in the values for S2, that tells me that S2 is equal to initial velocity, which was 60 times time, plus a half initial velocity times time squared. This is for S2, right? Displacement for the second stage. So the displacement for the total graph, all right, this is the total displacement over here, is equal to 300 plus what we just worked out. So this is plus 60t minus 3 over 2t squared. Okay. And finally, the time for my period between 5 and 25 did not start at 0, all right? Time 2 is t minus 5, and so we just need to change that into t minus 5. So displacement is equal to 300 plus 60, right? We're going to put in our t minus 5, right, because we did not start at 0. Right? And if you remember how x coordinates work, this minus just means a shift to the right of 5 units, which is exactly what we've done. We've shifted over 5 units. Instead of starting this graph at 0, we're now shifting the graph over 5 units to the right. Minus 3 over 2, and here we're going to have t minus 5 again, squared. At this point, we just need to expand everything out, and we need to neaten things up. And to save some time, I'm just going to give you the displacement function. After expanding these out, collecting like terms and simplifying, we're going to get displacement equal to minus 3 over 2 t squared plus 75t minus 75 over 2. So I can see that I have a quadratic equation here, right, with a negative a value, meaning that it's going to be a sad quadratic. It's going to be going up and then down, right? Now we are obviously ending at the turning point of this graph. That's the value at where the gradient is equal to 0. The gradient of 0 tells me the velocity is 0, and that's exactly what we want. Okay, so we are now ready to draw in our curve. Okay, it's not a very steep curve, it's a nice shallow curve. And we also have the function for our curve. And it's going to be a piecemeal function, meaning we're going to have a function for different stages, right? If we had to call this function something, all right, we could call it s of t, right? Displacement with respect to time, and it's equal to, right, now we need to specify that it's equal to something for different values, right? If we go back to stage 1, it's equal to 60t, and this is between 0 and 5 seconds. And going back to our what we've just worked out for the second stage, right? We have minus 3 over 2t squared plus 75t minus 75 over 2, and this is between 5 and 25. So if you wanted to find out the displacement, you'd have to pick a time value. Then you'd have to go to your equations and see, right, where does the time fall in? If the time is between 0 and 5 that I want the displacement, then I use 60t as my function. If I want a displacement for a time after 5 seconds, but before 25 seconds, I need to use this function here. Right? So that is the whole purpose of a multifunction displacement time graph. Even though the velocity changes, we can still create equations for separate parts of the graph in order to find its displacement at any value that we choose.